So, hi, STAT3004, STAT7304, can you hear me? No.
Yeah, I can hear you, Yanni.
Thank you. Hi. Okay, will take me a minute. Hi, everybody. Need to join on the other device. Okay. All right. Hi, everybody. Can you hear me now as well? I'm now through my iPad.
Still hear you, yeah.
Yeah, okay, good, thanks. So welcome. First of all, apologies for canceling the Tuesday at the last minute. I hope everybody's okay. So what we're going to do today is basically I'll answer further questions that people have, kind of like in a visit hour, but we'll see where we go with that. On assignment 1, on project 1, that's due next Wednesday, right? So you'll also find, by the way, weightings on the questions in project 1 up there. So,
hey, Yoni, is the weighting for the last question correct? It's got 40. Is it meant to be a 4 or is it actually 40?
No, 40.
Oh, okay.
40. I mean, the last question is really the projecty part of the project. And it requires you to do more. So I'll give some clarification on that. Yeah, I hope the weightings add up to 100. They should. And in addition to that, tomorrow I will have a visit hour. I think I said that on Blackboard on Monday, and the normal one on Tuesday. So I hope that everybody's kind of has enough support using that. And then Tuesday we'll continue with the activities. Let me show you where we'll go Tuesday. So I'll go here. So in the self-study guide. So even though we haven't spoken about everything here in the lecture, so we'll and this is relevant for project for this project. So I'm happy to kind of focus on that a bit on the stationary distributions. So we'll do activity 4 a bit more on Tuesday, and then we're moving on to continuous time. Okay, so for that I'll give kind of a complete lecture. So that's starting activity 6. So activity 6 deals with continuous time, Markov chains, moving onward, starting with very basic things such as exponential distribution, etc. Out of curiosity, has anybody gone all the way up to activity 6 and onwards in reading?
I've tried to, but I've still stuck on some of activity 3 and 4. I just find it really hard to get through all the notation and content. So it'd be good if you could actually cover it at some point.
Yeah. So is this TJ asking?
That's correct.
Yeah, so I mean, yeah, sure. You feel free to ask in the lectures and the visit hours. There's also, I must say, I mean, there's kind of a bit more of a broader spectrum in terms of study that we're doing here. So you know, you can understand some things and skip a bit other things and then go back to it later on, etc. The problem set that will be released for as a final pre-exam assessment will kind of give you an indication what the exam is like. And by the way, the exam, I don't think I published that yet, or I didn't say that. So the exam is a 24-hour open exam. It doesn't mean you need to open it to work on it for 24 hours, but there'll be a component that should be doable within an hour or two, and then there'll be a slightly more difficult component with less waiting. Okay.
So we have 24 hours to work on it then?
Yeah, you have 24 hours to work on the exam. It's an open 24-hour exam. And yeah, and so it's again with somewhere between 60 to 70% of the weighting on questions that are rather straightforward, and the other part is slightly more challenging. And then you might have a heavier tail in the time of working on it. So Isabel is saying I'm not seeing the weightings. Try to just refresh your website. Sometimes with PDF you need that. Oh, okay. And Daniel says little numbers.
Just wondering, could you update the profile with a bit more information about the exam?
Yeah.
Yeah, because that would be helpful. Because I was looking at some of the other maths courses, and they've got lots of extra information. Well, other maths and stats courses, I've got all this extra information about a paragraph at the end, just explaining it. Whereas your ECP is like really brief.
Okay, I will. Yeah, so basically I will, and it'll say that it's a 24-hour exam and what materials you can use and what you're asked not to use.
And is this exam, I'm assuming it's not invigilated then?
It's certainly not invigilated.
Okay, thanks.
Yeah. Okay. Other things? Okay, let's go on to the project. This is here without the weightings. This is just the version I'm scratching on here. Does not have the weighting. So yeah, if somebody can't see the weightings, then I see some things in the chat. So sometimes if you open a new incognito window on your browser, and then it'll force it to refresh. That's one way. Okay, so yeah, but basically the point with the weightings is there's 40% on the last question, and the rest are all relatively small, and also some of the harder questions get a bit less weighting. So I've seen there's a lot of interaction, mostly with Jack Thompson has been very, our tutor, one of our two tutors has been very useful on Piazza. Are there any specific questions that you'd like to ask about this project? Let's just get a discussion going.
I think for question 6, it'd just be good to get a bit more insight as to what actually needs to be done, because I think it's kind of seems to be straightforward just to put a computer model together to crunch all the numbers, but then what from there? Okay, fair enough. So let's actually read question 6, because that's a project-y part of the project, right? Let's do that. So I'm just going to read it with you. So we consider a slightly more involved modeling situation. Okay, it's clear that it is. And the steady state here is a critical thing. So when we assume a system is steady state, then we assume it's been, well, it's either miraculously started at steady state, but that's just a mathematical abstraction, or more realistically, we assume it's been running, or we can assume it's been running for an infinite time, but that's also a mathematical abstraction. But practically what we mean is we're going to analyze it over a period that's long enough, and there aren't significant changes during that period. Now, of course, with something like a pandemic, that's not the case. A pandemic is all about transient changing behavior, but with a steady state assumption, we might, what we have in the back of our head, I'll just, how do I add another page here? Sorry, one sec. So what, oh, here I have another page below. So what we have is maybe something like this, where on the timeline, this is the pandemic, and it's going maybe like this. This is an infection in general, and we are speaking about it in, say, this period, for example. So even though there's slight changes during that period, we'll assume that it's in steady state. So assume a small motel in a regional town with capacity up to X0 people. So X0 here is in a sense a decision parameter. the governing body of that town. How many people can fit in that motel? There's pandemic, travel restrictions, security measures, yada, yada, yada. So they're supposed to quarantine as they land, as they arrive. Assume there are dozens of arrivals to the town per day, and hence there's always enough demand on the motel. So a slightly more involved problem would have had the fact that from time to time you actually, maybe you have a weekend or you have seasonality during the week, etc., and there's kind of less arrivals or more arrivals or whatever, and maybe you don't have enough. But here the motel is standing and is always accepting enough people. Okay, that's kind of the thing. So you don't need to worry about lack of people. You always have, if you want to put, let's say the motel is empty and you want to put X0 people in the motel, you can. Okay, so that's a simplifying assumption. One of the things you're supposed to do in the end is actually kind of describe the assumptions, etc. Further assume that we're in a long period of time during which the pandemic, where the probability of new arrivals by COVID is eta 0.05. Luckily, we're certainly not in that state, so it doesn't seem in Australia, and perhaps not anywhere else in the world, but maybe. People don't know actually the prevalence of COVID, of course, and that's a big question in other places. So that means that we're here, and this is our motel. So out of every 100 people that come, about 5 people have COVID. Okay, and 95 don't. Okay, that's obviously what this means, and this is again relevant for kind of being within this steady state period where eta does not change. Okay. Also assume there is not any immunity to COVID-19. This is mostly wrong. What does this come to say? You don't have people that come and are already immune. Okay, so you don't have people that already have antibodies to the supposed virus, and then they don't get infected. Okay, so everybody who comes is either infected or not. Okay, so we call that susceptible or infected. There are no removed people that come. Yeah, stop me at any point, please, if this is not clear. Okay, the motel's policy managed by local government is to accept these X0 people, individuals, all at once. Okay, so every time a motel kind of opens the gate, says, okay, new batch, come all at once. Okay, where X0 is the decision parameter upon arrival, and then test them for COVID. So we might have here, like, this is day T. Okay, so all the arrivals kind of arrive. You got X0 arrival, and here by day T plus 1, they will have test results. Okay. But they've already, in this day, they're sitting in the motel, okay? Playing poker or whatever they do. Okay, I don't know what they do. They're just there, okay, behind that scratch. So you've got the X0 and their and results are announced in this day. So when the results are announced, if all the X0 are not infected, then they're told, okay, guys, we checked all of you, you're not infected, you can go home, okay? Or you can go to where you wanted to go in this town, okay? They're released. And immediately, because we assume this thing that there's kind of infinite arrivals, okay, dozens of arrivals, which is enough, okay? Then we're gonna put in a new X0. I mean, I say that dozens is enough because we're going to look at small values of X0. I mean, all these models, the Greenwood and the Reed Frost, were about small kind of places. Okay, so if they're released, we get a new batch. So it's at this point in time is that you got kind of a decision. Are they going to stay? Because one or more. Oops, you probably maybe can't see this noise. You can see this. Stay. Because one or more were infected, or are they going to leave? Okay. If they leave, the process repeats itself and you get a new X0 at that point of time. If they stay, and they start a course of staying together. Okay.
So Yoni, my understanding was with the people that stay, the infected people are removed from the group.
Yeah, but right. So they're removed, but they've already kind of that's where you need to be delicate. So they've already those removed might have already infected the stain. I agree.
Yep, but the people that are removed, are they replaced by new people? So if 3 people are infected and they're removed, do 3 new people come in? No.
No, good question. Let's read, but no. The answer is no. So let's read and see. It makes sense, but and then hence clarify that. But good you're asking that. So the batch is going to kind of reset itself only if there was no infected. Okay, but however, if there is an infection in any one of those X0 people, then they all stay in the motel until there are no more infected in the motel. Okay, so they all stay in the motel, but they're removed in the sense that they're let's read this. In every day of their stay, they're tested again, and those that test positive are removed. Okay, so it's in this first instance, yeah, I guess in every day. So you need a bit of interpretation, and that's your point. So this first day upon arrival, they arrived, and you had, say, let me clean this up so we see. So you had say 2 people sick and 8 people healthy. Okay, so those 2 are then going to be removed, and the 8 healthy will stay the next day. But the thing is that those 2 might have already made some of these people sick as well. Okay, so from those 8, maybe you might have some sick and some healthy, and those will be removed, etc. So it goes naturally on both the Reed Frost and the Greenwood models. Okay, so if there's infection in any of them, they stay in the motel until there's no more infected in the motel, and every day of the stay they're tested again, and those that test positive are removed. They're taken to some other serious place. Okay, whatever that is. Well, those that are not positive remain. So basically, you're running through a similar course of a localized disease within a household, similarly to what these 2 models that you worked on the other exercises work. Okay, so I have here a chat. So Naaman Pearson, we're blessed. That's a nice lemma you have there, Naaman. It's not your real name, is it? Okay, maybe I don't want to. So the Naaman Pearson lemma, hypothesis testing. Okay, if all X0 get infected in the first day and test positive, so what Naaman is saying, if all X0 get infected in the first day and test positive straight away, that does not mean they stay 1 day or 2. Will X0 will be removed on day T1 and replaced. So if they all test positive, that's it. They've all been taken away and we restart. Okay. So what Naaman is saying, if all X0 get infected in the first day and test positive straight away, does not mean they stay 1 day or 2. No. So they're gonna follow this type of course. Okay. This type of course that you see here. Okay. And then Naaman asks, will all X0 infectives be removed on day T1 and replaced by X0 new people on day T2? Yes. So if they're all positive, then yes. Okay. Now, if there are multiple interpretations for this, then, so to this story, it might not be that there's exact one model for this story. So we'll accept various interpretations. With discrete time modeling, one of the things that happens is you need to kind of say within a day what happens first. As you do first test, you first remove, etc. So you need the sequence of events within your point of time, because you just have discrete point. Okay, did that help? Okay, you're welcome, Naaman. You're not revealing, is that your name really, Naaman? It's not like we're putting this on YouTube or anything. Okay.
In one of my other classes, there's a person called Garobi, so,
Oh, okay, you guys are a bunch of nerds. All right, so.
Yeah, do we get a new batch of people as soon as the hotel is empty?
Yeah, so you can do 2 options. So that's, I'm not sure who asked the question, but the question is valid. So when they get removed, do you get a new batch of people or do you move to the next time? Choose whatever is better for you for the modeling, but your Markov chain that you're modeling needs to needs to model that. So I believe that getting a new batch immediately is probably easier. So they removed immediately a new batch. Otherwise, your Markov chain would need to, and your results would be different, right? And you need to kind of model another state that you're in this day where everybody got removed and you're waiting for the next batch. Okay. So you can to answer, say there's kind of immediate filling up. And that agrees with Isabel's question. Wouldn't it be replaced on the same day they got removed? Yes, you can do that. Yes. Okay, I mean, this is a modeling question, and there's sometimes several interpretations, and they affect the results.
Yeah, cool, thanks.
Okay, good. All right. Further infections may occur because those that tested positive were there for a whole day before. Okay, and that's what allows us to use our models that we studied in the previous ones. Assume the infection inside the model follow the Reed-Frost model with P 0.1 and beta 0.05. So those, I hope it's clear to everybody. So those models, we hardly spoke about P and beta in most of the authors of the book. Hardly spoke about it with the exception of kind of in this page 106. So it's kind of nice to quantify the two parameters that actually cause infection. So often people just speak about infection, but it's a combination of meeting, and that has to do with P, and it's a combination of the infection, and that has to do with beta. Okay.
So Yoni, when you actually put in the P and the beta into that formula, alpha is like a 99.5, I think, %, which means that it's not impossible, but very hard for someone else to actually get infected in the motel. Is that right?
Is it 99.5?
Yeah, it's really high.
Yeah, I think I took that into consideration, and if the results just don't make sense with that, then if somebody could send me her or his answers, and I'll update that. I mean, 99.5, but then you have x0 people, right? So x0 to the 99.5 to the power x0 becomes smaller.
Oh.
Right. That's for a single person. Yeah. Okay. So, but that's, maybe I've set this up wrong, but I don't think so. And it set this up wrong in the sense that the results are numerically hardly, that for this range of x0 that you won't get a difference. Okay. And again, I'll be very flexible in marking these. Basically, I want to see some, and I'm marking them, not the tutors, just so you know. So I want to see here we'll speak about how I am expecting to see this roughly. Your goal is now to determine the long-term expected rate of infections per day per person. And I was asked about this, and actually the new version just says per day. Okay, so Nicholas asked me about that a week and a half ago. So yeah, that's per day. That's updated in the updated version. Okay, so how many infections actually come out of this place per day? I mean, if x0 was 1, so if you just put a single person in the motel every time, then your rate of infections should just be eta, which is 0.05. Okay, because there's no chance for people to mix these guys in the motel that are, playing poker and pool and pokies and having a drink and disco machine and all that, and they're touching each other and all that. So, it's going to be the same. But if you increase x0, then you expect to be above this number. Okay, so quarantining, I mean, the main point here, and this is actually, this is somewhat relevant to discussions that are happening locally in different places around the world. Very analogy type of way, quarantining actually increases infection. Okay, I mean, for example, in South Africa, people are now being taken, homeless people are being taken and put in camps in a quite strict manner, and of course it's clear that these places are breeding infections. So we're going to try to quantify how. However, with this motel and x0, the rate resulting should be bigger. So now carry out the partially numerical. Let's discuss what that is in a minute for x0 going from 1 to 10. Okay, so
And it might be that what TJ just said, that if alpha is so, I don't think that 99.5 is a problem. But if it is, then, and you see it, then we might need to just adjust these parameters a bit, okay? So increase P or increase beta. And I'm flexible with that, but we'll also communicate about that. Feel free to use explicit computation, numerical computation, Monte Carlo, some combination thereof. So basically, when we say explicit computation or numerical computation, so explicit computation, it's probably not so easy. Okay, so explicit computation, you're going to have some underlying discrete time Markov chain, and you'll compute its stationary distribution explicitly. Okay, so you have a closed form expression. I mean, we've done this for 2x2 chains, or you can do it for specific chains. You can do it for birth dash chains or for others, but it's probably hard. Numerical computation, you'll solve these equations numerically. Monte Carlo, you'll actually run a Monte Carlo simulation of this Markov chain. Doing both numerical computation and a Monte Carlo simulation is probably good, because you see your results agree from two angles, okay? And you've done this in some of the questions above. Okay. Now, if you find using the Reed-Frost model too difficult, you can use the Greenwood model, and I think that's fine, because also in the Reed-Frost, you need to make an assumption, right? So you need, well, it's for partial marks, but I'll be very generous. Okay, so with Reed-Frost, you need to assume how many people were at first, what was your Y0. But it's actually doable, because Y0 are going to be the infected people that were here, that were infected with COVID initially. In any case, you could start with Greenwood and then kind of upgrade to Reed-Frost. Okay. Present your analysis in the form of a standalone report. So please note a different file. It's just kind of 1 or 2 pages at the end of the PDF containing your other work, right? So your PDF document will have questions 1, 2, 3, 4, 5, and then 6 is like a little report. Okay. Here in this motel, we have this assumption, etc., and here's a computation. Just the key results first. So I mean, the most important key result is just a relationship between x0 and the rate per day. Okay, where eta is 0.05, and you're going to see something that goes up in one way or another from x0 going from 1 to 10. Okay. But then afterwards, some analysis. Okay, state what part of the analysis is unrealistic in your view. I mean, because this is kind of, you could say, well, this is at least I'll answer the question on the chat in a second. You could say, this is a potentially useful thing. It says, hey, if you're quarantining people, then you know, the more people you quarantine in such a regime, the more infection you're actually going to introduce to the town. Now you can say that, you know, they're quarantined, so they're not going directly to the town and they're speaking with other people and infecting them. They're going to some other quarantine section, but still there's suddenly more patients in the town. Quarantine section, like the care section. Okay, let's go to the chat. So Xian Tang says, so if there are no people tested positive and leave, all people are tested positive and are removed, the hotel will be filled by X0 new people on the next day of the test result release. Will happen the same day when the people leave. Okay, so I mean, that's a key, again, Xian's question was in a sense asked before, and it's a key thing where you choose, right? So you choose if you want the X0 people to come the next day, or you say, well, if they're all released, you fill up again. I think filling up again is fine. Okay, but if you did it with having a next day, you need kind of another state in the Markov's chain that remembers, hey, I'm in the state of everybody's now left and people are going to come the next day. Okay, and Lawrence repeated that. Okay, thanks, Lawrence. All right, so that's that. And with this, I want to do a little kind of exam. Are there more questions so far? I mean, I'm going to give a bit of a kind of a general, another thing related to computing rates associated with Markov chains.
Perhaps what you're about to do will answer the question, Yoni, but just to be very, very clear. So with what's expected, we do the Monte Carlo simulation, fine. Are you then expecting that we kind of put together a matrix of what the transition probabilities are and then also attack it from that angle as well? Yes.
I mean, your Monte Carlo simulation, it's true that it can
B, perhaps not using transition probabilities, but only kind of as a stochastic recursion, right? But it's better, it's nicer to have explicit, well, numerical computations, okay? That, you know, show your matrix. Okay, I mean, you're going to have here a family of 10 matrices, and they're maybe going to be 11 by 11 or 10 by 10 or something like that. But if you're actually using Reed-Frost, they'll be bigger. Okay, so you don't have to show everything. A good report is a report that's reproducible. Okay, so you have kind of, and you guys don't have to do this perfectly, but you need to do it perfectly to get perfect marks. Okay, so, but again, I'll be generous in this. So a good report has kind of an executive summary at the top that just says, this is a result, this is a graph that the health manager at that fictitious town can understand. This is, if you quarantine with this is how infection rate grows. Okay, full stop. That's it. But then below comes the appendix, where the STAT3004, STAT7304 graduate that is helping that health manager is checking, oh, are these assumptions of these people sensible, etc., and what they computed. So ideally, it should be reproducible. Okay, does that kind of help?
Yes, thank you.
Okay, yeah, it's open-ended. It's a project. That's why we called it a project.
So is there a specific structure you want the report to have? Like you said, it starts with the executive summary. So what are the other sections?
No, it's no longer than 1 and 2 pages, right? It's just going to be nice and clean.
But should we have like so you're not really worried what the sections are, just as long as it explains everything.
Yeah. Yeah, open-ended in that respect. I mean, there are many ways to do this.
So it's not like a scientific experiment where we have method, results, discussion, or anything like that.
No, more like an applied math section, right? Yeah, it's. Yeah, I mean, basically, if you have notation on there, it should be defined. It can be in handwriting, by the way, right? Or a combination of handwriting and not handwriting. Okay, so don't get stuck on formatting. But when things are clearly defined, one picks up the document and says, oh, what's this? Oh, okay, that's eta, that's x0, that's 3 sentences describing that. And then, okay, what result it is, we define the Markov chain on these states, the Markov, each state. Whenever you define a Markov chain, it's important that you say how states in the Markov chain relate to reality. Okay, what is state I in the Markov chain? And we compute a stationary distribution on this Markov chain and used it to obtain the answer in this way, or we did Monte Carlo or the combination. Okay, does that kind of help? And if you can, oh, and that's a good question. So Matt's asking, are code snippet counted? Look, if you want to stick a code snippet, you can, but not necessary. I mean, it's going to be hard to stick in 1 and 2 pages the code snippets. Right, but if it's quite straightforward to solve a linear system of equations, and or to simulate from a discrete time Markov chain. So if you just, from my perspective, this is kind of, oh, that function that does that. Okay, we don't need that code. I mean, if there's 1 or 2 lines of code that you think make it cleaner, go ahead and add them. Okay, and Lewis says, so do you want us to attach code snippets? No, please don't. I mean, just a PDF file. No, I just won't have the resources to look at that. But you know, I mean, if for those of you that are hardcore, put it onto GitHub and have a link to GitHub, and that never hurts actually. So you can do that, and you know, but it's for you as well. I mean, it's another repository in your GitHub.
Is that all questions that we should not be supplying code for, or just the one at the end? Because usually in other courses I'm usually told to supply the code because I want to check that we haven't plagiarized and we haven't copied each other's code, and so I'm just a bit curious. So you don't want any code at all then?
That's again a good question. I mean, you can, for example, if we look at this, run a Monte Carlo simulation, you can put code, but there's no page limit there, right? So it's like a question, you flip through a few pages, see code, okay, and quickly see what you did in 5. But 6 is aiming for kind of something neater, right? I mean, this is, so, you know, the standalone thing. Okay, so yeah, please, if you can supply the code to the previous one, please do. I don't make it mandatory.
But if we do supply the code to the previous ones, do you want an appendix or?
No, just straightforward, clean.
So it's okay if we put the code for say 1 to 5. You just don't want it for 6.
Yeah, unless it helps the message in 6.
All right. Okay. Thanks.
6 is nice and dandy. 1 to 5 are your typical assignment questions that are like a pain to look at. And you look. It's important that it's linear, that you kind of go through it.
So 1 to 5, it's more about checking that we do. So your 1 to 5 we can. So with 6, it's basically the focus is on the report. We're being marked on the report, not how we did it. I'm guessing.
Yeah, but it's also the modeling, etc.
Yeah.
You still need to do it. I mean, with all this semester is about you for yourself in a sense.
Yeah.
It's you for yourself with the help of the teaching staff and your mates, which is kind of maybe a good thing. Yeah. Okay. All right. Don't plagiarize, please. Other questions? Let's get to a little example. So I'll just do this here. So assume we have a weather chain 1, 2, 3. This is exactly what I did in one of the visit hours. So apologies to those that have already seen this. So you've got this kind of transitions between 3 states where weather is in state 1 or 2 or 3. I'll pause for a second and look at Xian's question. For question 5b, do we need to consider P0J, which are zeros in the communicating class, or can we make an assumption that they are not a count for communicating class, include them in the state space, so seem be included in the communicating class? Okay, let's answer Xian's question a second, and then I'll answer other questions after I finish this example. So so the thing with the communicating classes here, you do need to consider, you treat the Markov chain and you formally say what are the communicating classes, okay? Or you try to describe it in a compact manner if you can. So P0J is a transition from state 0 to J, and having zeros makes a difference, okay? So these are highly transient Markov chains, these Reed, Frost, and Greenwood Markov chains. Once you leave a state, you often never come back to it. So you'll see that the communicating classes are big. I mean, this is not one of those cases when you have a few communicating classes. Big, I mean numerous. There are many communicating classes. I hope that helped. If you just want, side example, so just look at this Markov chain, okay? Just a little side. So you got a state here, you can go from it to itself with probability 1. You've got a state here, you got to it with probability half, and you got another state here, which you go probability half, okay? This is state, let's call the state 0, state 1, state 2. Okay, see this Markov chain? You can call this a pure death process, okay? You're in state 2, and that means there are 2 people in the system. You've got probability of half of staying with 2 people in the system, and there's probability half of 1 person dying. And then, so that's how you move here, okay? And then, there's another chance of half of 1 person in the system and another 1 person dying. Okay, what are the communicating classes here?
Well, it's everything apart from sorry, they all communicate, but 0 is recurrent and everything else is transient.
So 0 is indeed a recurrent class, but this is a class and this is a class actually. So each of these is a class in its own right. So for 2 nodes to be in a class, we need to have possible transitions from node I to J and from node J to I. So if I to J in the class. So this doesn't hold. So if we look at 1 and 2 and we ask, are 1 and 2 in the same class? We say no, they're not. I mean, yeah, you can go from 2 to 1, but you can't go from 1 to 2. So you've actually got 3 communicating classes. Each node in its own right is a communicating class. Okay, so if you'd have an arrow going back here, then you'd have these would be the communicating classes. And I agree that this is a recurrent class and this is a transient class. transience or recurrence is a property of the class, because if one node is transient in the class, or if one state is transient, all the nodes are transient. Okay. So that's the type of thing you're supposed to do with Reed Frost and the Greenwood model and those communicating questions. Okay, and of course you don't have that arrow back in Greenwood and Reed Frost. I mean, people just leave. Okay. All right, back to this example. So in this example, let's now, and let's say that all these, so we have a matrix P, transition probability matrix, okay? And let's just for simplicity even say that all the entries are positive. So I'm putting here like this thing means this doodle here means it's strictly positive, no zero. Just side question, what are the communicating classes now in this matrix, in this discrete time Markov chain?
Well, if they've all got positive probability, they're all communicating.
Right. So, I mean, all states communicate, and hence there's one communicating class. Okay, that's okay. So there's one class. Okay, one class. So this is called an irreducible discrete time Markov chain. It has a single class. Okay, so we're not even worrying about these class issues.
And they're all recurrent as well.
Mm-hmm. And they're all recurrent. And in our Hotel California here, then they're also all recurrent, because people die, but then the next batch is going to arrive. Okay, so this problem here took the kind of those transient models and put them in a kind of in a repeatable setting. Okay, that's what happened in this problem. Okay, so we're back to this issue here, and what we're speaking about now is first of all, you can say, let me just write a few things. So let me call let's look at this thing. I'll write sum t from 0 to infinity times the indicator of xt. Xt is this discrete time Markov chain. Okay, xt is a state, so xt takes values 1 and 3. Xt equals, for example, I'll start by putting 3. Okay, so this indicator under variable here gets a 1 whenever we're in state 3, otherwise it gets a 0. Okay, if we just look at it like that, then this random variable here, or this series, diverges with probability 1, and hence this random variable equals infinity, because we're going to be in 3 infinitely often, because 3 is a recurrent state. However, what we can do is we can put here something like, let's do t minus 1. Okay, the reason I put a t minus 1 is because I have here a 0, and divide this by 1 on t. Okay, so this object here is the average over time units 0, 1, 2, 3, up to capital T, or t minus 1 in that case. Okay, and it says what proportion of time during these time units, okay, what proportion of time, that's the division, what proportion of time were we actually in state 3. Okay, now the theory of discrete time Markov chains says that as you take limit t to infinity, this thing is going to be pi 3. Okay, where pi 3 is the stationary probability of state 3. So that's fine. I mean, and you know how to calculate pi 3. So to calculate pi 3, you'll put a system of equations pi 1, pi 2, pi 3 times your matrix P equals pi 1, pi 2, pi 3, and you'll also have the other equation sum pi I equals 1. Okay, so you'll calculate the stationary distribution. So a meaning of the stationary distribution is this thing. Okay, and of course, instead of 3, so far as I'm just reviewing stuff, I could have put here a 2, and this would be pi 2, or more generally, let me just put here an I, and then put an I, okay, for I equals 1, 2, 3. Okay, so that's fine. I mean, I assume there's no surprise to you. Here, you know that this is one of the meanings of the stationary probability on state I in a recurrent state. However, what if I want to ask a slightly different question? I want to ask now, what are the every time? So let's say 3 is bad weather, okay, and 1 is good weather, whatever that means. Okay, generally we still think that bad is rainy and good is sunny. Okay, unless you live in a desert most of the time, right? So we think we ask ourselves, how often do we make this transition, this one, okay, the transition from bad to good weather, okay? How often do we make such a transition? So we might ask ourselves, let me, I've messed this up, it's very dirty. I'm just gonna erase it. So we might want to ask something else. We're not asking now what's the long-term proportion that we're in state 3. We're gonna ask what's the long-term proportion of transitions. So the question we're actually asking is what's limit t to infinity of 1 on t on some t going, let me now just write 1 to t if you don't mind. Okay, just don't have to do this, but of xt equaling 1 and xt minus 1 equaling 0. Okay, so this is the thing we're asking. So each time for every t, we're going to turn on this indicator on when we made a transition from time t1 minus t. Sorry, what am I got here? Not 0, but a 3. 3. Okay, let me fix that. 3. So when we're going from time t minus 1 to t, and we're making a transition from state 3 to state, why not? Why don't you want to draw a pen? From state 3 to state 1. Okay. So how do we compute such a thing? Okay. Well, one thing we can do is we can do some conditional probabilities and actually see that this thing equals pi 3 multiplied by p 3 1. Okay, and you'll get that by splitting this thing using some conditional probabilities. Now notice just a bit of a warning here. I put here something without any this is kind of a number, and these are random variables. Okay, so I allowed myself to put the random variables here without actually saying using expectation or probability. If at this point you feel a bit more comfortable, then you could put an expectation here on this. Okay, so you can put an expectation here, or alternatively move it outside. Okay, you can put the expectation here, or alternatively move it outside. Okay, but it turns out that this is going to be true even not at expectation. It's true almost surely. So this thing is is random for every if I forget the limit, it's random for every capital T because it's an empirical average on the time T's. But if I take limit to infinity, it's actually going to converge to that almost surely. But think of it in terms of expectations, if you will. The more important practical point is that what you're going to do is you're going to say, okay, pi 3 is a proportion of time. Where did this go? Oh, I erased that. Oh no, pi 3 is a proportion of time that you're in state 3. And then P31, yeah, P31 is this entry, P31, that's P31. That's P31 is the probability of going from state 3 to 1. Okay. So this is how you can use the stationary distribution to compute such a thing. Now, there's more things you can do. You can say, what if every time that I go here, okay, is that clear so far? I mean, this is kind of a usage of the stationary distribution, which something slightly similar to that you need to do in question 6. Okay. Now, you can ask something else. You can ask a slightly different question. You can say, every time I go from state 301, say from rainy weather to sunny weather, I'm gonna pay positive $2. Okay, or I'm gonna get $2. I'll just get positive 2. Okay, I get positive 2 reward points to my general well-being, my general feeling. I'm like, yes, it's going from 3 to 1 with positive 2. Whereas if I'm going from say 3 to 2, if I'm going here, let me make that like red just to kind of be consistent or whatever, then let's say I'm going to get like only a positive 1. Okay, so the weather was really crappy, and now it's kind of got a bit better, so I only got positive 1. Whereas let's say if I make such a transition after a rainy day and I have so much yearning for a nice good day, then I get like a negative 5. Okay, negative 5. So what you have here is kind of a reward structure associated with such transitions. Okay, so the way you would look, and again, you can now look at the long-term average reward. You can write all your reward as something that would look a bit like this, but I'm just going to write what it's worth. So this is kind of a really straightforward way of doing it. You're going to say, if I'm at pi 3, okay, and that's pi 3 in general, I'm going to multiply this by all the terms. Then with probability p31, I'm going to get a positive 2. And then with probability p32, I'm going to get a positive 1. That was just positive 1. And with probability p33, sorry, I'm going to get a negative 5. Okay. So when you're thinking, that's that's something that you'll do times pi 3. And of course, if you're paying for each of these transitions and you have reward structure, then you can add plus pi 2 and you'll have the associated reward structure of transitioning out of state 2 and similarly out of state 1. The word I'm saying is a reward structure. It's kind of just a payment associated with transitions, etc. So if you're thinking about this thing and now you're going back to your Corona hotel, right? So whenever you have people departing, those people are accumulating to the reward, so they've kind of got more and more sick. Okay, so you can use that type of reasoning to answer that after you've calculated stationary probabilities. Other questions about that? No? Did I bore you all out?
No, that was good, Yoni. I think, well, I'll just think through it a bit more, but you give us some insight there. That's good. Thank you.
Okay, nice of you, PJ. Thank you.
Yoni?
Yes.
Sorry, I just wanted to quickly ask, could you maybe remind me again just what pi 3 and pi 2 refer to?
Yeah, so they're the stationary. So when you go to say SP1 here, and you go to stationary distributions, okay, so they are the long-term in your reducible finite state Markov chain. That's what it is. They're the long-term holding probability of a state. Okay, they have different meanings because they're in the invariant distribution, the stationary distribution, the limiting distribution. Okay, so it's when you look at this. Nope, we were here. When you look at this weather chain, okay, sure, you have here transition probabilities from state I to J, but what proportion of time are you actually going to be in state 3? So that's pi 3. And they're obtained by solving this system of equations. Okay. So that, in a sense, it's for long-term behavior, for stationary behavior, it's the most important measure, in a sense, or it's the first thing one would compute. A lot of Markov chain analysis deals with that. But all the other problems in the homework assignment were not about that, because the nature of epidemics is actually, well, depending what type of epidemic, but in the ones that we had here were actually not of the stationary type. there are stationary, there are epidemics of the form of SIS, kind of like, you know, flu, that you can get sick and get healthy and get sick and get healthy, get sick and healthy, and then stationary description would work. But a stationary analysis is useful here to get kind of a rough estimate of what you're going to get in steady state. Other things?
Sorry, Yoni, just one other question. With question 4D, which is using the probability generating function to reproduce what's in the book, I think it's quite straightforward what needs to be done there. Well, I think it's quite straightforward how to do it, but it's very computationally intensive, especially if you're doing it by hand. What are you actually expecting? Can we just put it into, say, MATLAB, get MATLAB to do all the derivatives and everything and calculate just the end probabilities and just tell you what the end probabilities are, or what do you want?
So, I mean, there's no, first of all, I put very low weighting on that because it's just slightly more, you know, you need to be slightly more mature as you're kind of reading through the explanations here. Okay, so it's about what they mean. I just wanted to, the reason I put it in, I wanted to have a question that kind of connects to stuff that we did in the start of the semester that has to do with PGFs. Okay, so cut corners if needed in terms of, you know, taking derivatives using a symbolic computation tool. If you
Thank you.
MATLAB is typically not the best mathematical or Maple, but if you manage with MATLAB, it's fine too. Other questions?
Yanni, I just wanted to ask about 3D. So I mean, so for 3C, you have provided us with like a matrix equation that can compute the expected value. And I was just wondering for 3D, are you expecting us to come up with some kind of a matrix formula, like a formula to calculate the expected value of Y, or can we use the expected value of X to sort of calculate the expected value of Y?
Okay, so the latter thing that you said, using the expected value of X, is a natural thing to do. And that's been asked before in one of, but that's fine. So and you know, you use conditional expectation, but here, since this is, you know, since we did this rather cumbersome computation with this bilinear form of squashing the matrix PT and taking the expectation of this function and then doing that, then if you're able to do that, then better. That's what I mean by similar. Okay. Not the end of the world if you can. You just supply the more straightforward proof. If you do that, then the hint is what you're going to do is on that right hand function, you're going to put in something different here. You're not going to put the actual expected state. You're going to put, it's going to be in a similar vein to these computations which is just shown here.
Okay. Right. All right.
Hey, Yoni.
Yes.
I was just wondering, I understand what a Monte Carlo simulation is in part 6, but do you mind just explaining what you mean by a explicit and then a numerical computation? Yeah,
sure. So a Monte Carlo is, okay, you understand. An explicit is if you're somehow able to write the system of equations, okay, this bit here got very wonky, but it's pi 1, pi 2, pi 3. Okay, this, okay, and actually have a formula for pi I, which is like, you know, an expression that has in there p and beta and x0. Okay, these are the three numbers. Okay, if you're and eta. Okay, these are the four model parameters, if I'm not mistaken, right? If you're somehow able to do that, then great. I doubt you can do that. If you can, it's great. Then a numerical computation would take this matrix P, okay, and would basically acknowledge that this is a system of equations and solve the linear system of equations. Okay, just like in the, look at SWJ1, you know, that chapter, that example.
You're ignoring your phone and focusing on your laptop. It's usually the other way around.
Right.
Are you speaking about me?
No, I think someone else's mic is on mute. I think someone called Kenton Lamb mic.
That's okay.
So you're basically saying that the numerical computation is simply just somehow finding like a transition matrix for whatever relevant thing we need to find, and then computing pi p is equal to pi, and then doing what you were just saying before, basically.
Yeah.
Okay. Brilliant. Thank you.
Okay. All right. So visit hour tomorrow at, was it 2 in the afternoon? It's a Shabbat, but we can do that. You don't have to come, obviously. Similarly, Monday, similarly Tuesday, and then Tuesday on the lecture we'll start pushing into. We'll do a bit of more of activity 4, and then we'll try to head into activity 6. Okay, and the assignment 2 I'll push, project 2 I'll push a bit forward also. So meaning I'll delay the submission by a similar quantity, similar date. If there are no more questions, so anyway,
Hey,
I need to
Yanni.
finish. Yeah.
Just one more question that I wrote in the chat. It was like for questions like 4B and C, they're worth 5 marks, but simply like require you to calculate a numerical solution. Given that you don't really need the code, is providing like a justification and what the value means and how it compares enough to obtain those 5 marks?
Yeah, I you know, it's not that I don't need the codes. I mean, put the code if you can. You know, I mean, it's, but it's not. I'm just not explicit about it. So you know, you still need to do it. Yeah, a lot of the semester is about honesty, right? So and you needed to do it for your specific alpha. Okay, so you each have a specific alpha. Please choose it to be an irrational number. No, I'm joking. But you each need your alpha, or it doesn't have to be unique alpha, but an alpha.
Yeah. Okay.
All right. Thanks, Luis.
Thank
Other
you.
questions? Okay, so lecture's over. Now I just want to show so everybody can leave if they want, but those who want to stay, I just want to share something from the my personal stochastic processes world. So I've been, so feel free to look at this. You can check out this website, safeblues.org. So I've been intensively working with a bunch of talented people on this thing. And there's a lot of Markov chains actually in our paper. So safeblues.org, I'll put in the chat, safeblues.org. Lecture is done, so if anybody wants to leave, feel free to leave, as always, anyway. So you could look at our draft paper that we put on, and we're pushing things to the world. The main idea is that if you look at the state of the epidemic in a given country or region, and in parallel you actually run all these other blues things, which are kind of virtual viruses that are safe, that go from one person's cellular phone to another, not like viruses but just tokens, kind of simulating virus movements. Then if you look here at time 115, then you know immediately the state of those virtual viruses, but you actually don't know the state of the epidemic, because with epidemics we have a big delay in actually knowing the real state. It's hard to measure an epidemic. And then you can use some machine learning methods to predict. You see this blue line is a prediction. And then as time progresses, you see that the prediction, which now became green, is not so bad. That's at least a principle. So it's a general method that we put forward. Feel free to look at this. Don't let this bother distract you from your real obligations. The thing is that I want to just relate to this course is, if you look at our set appendix C, then we have testbed models on which this was tested. This is of course far from reality, but they're kind of a proof of concept, and they're all stochastic process models in a sense. So each of these models are models that you should be able to understand once you finish this course or in the middle. Specifically the second one is, for example, an SIR model with a continuous time Markov chain and some movement on a tree. So that's it. Just a little bit of an advertisement to research that I've been spending a lot of time on. So thanks for staying, and see you on the visit hours or Tuesday.
Thanks, Yannick.
Bye, guys. Bye-bye.
Yes.
Yanni, sorry,
Go
do you
ahead.
mind if I just wanted to ask you, for 5, I think for the Monte Carlo bit in question 5, is it fine? Like, I feel like it won't make a difference, but the initial why not? So because it's the Reed Frost model, so so for 5D,
Good question.
would that, I don't think that'll matter, right? Like for the
It will.
probability.
It will, and your question is valid. And I think TJ asked us in the visit hour, and there were very few changes to this update with the weighting. Some Y0 of your choice.
Oh,
So
Y0.
I've just. I mean, I'm sorry if you spent time on this previously and wasn't, but because it was missing, I should have said some Y0 of your choice.
Oh,
okay. So the Reed Frost model, if you start with many people sick in the house, it's different than if you start with few people sick.
Right. Yeah,
right.
That makes
So
sense.
good observation. Okay.
Okay.
All right. Other?
Yeah. Well, I was just curious about this content in general. Is this like, obviously these models are used for like it says small populations, but what do they use for? What do like epidemiologists use for like large populations and things like that?
Right. So the next model that we'll deal with, which is chapter 3 of EM, but we'll do some continuous time Markov chains, is the stochastic SIR. So that's the big population.
Okay.
This one is used for households. You could still, it's important to, but it's kind of interesting because you cannot just use differential equations for households. In households, things are very discrete in nature, right? So if you, just out of curiosity, like to quench your curiosity, if you look briefly at section 4.3 in EM4, then it's taking these models, but then averaging them over a population of households. So for, one household has, where you put a prior distribution on alpha, basically. Okay. I mean, you can think, we did this for one household, but, if we had like another project, or if we do this again next year, maybe it'll be like, you have an infinite number of households, and the density of the parameter of each household is F alpha.
Right.
Okay, so it can still be used for seeing. So imagine everybody locked in due to COVID. Okay, and some households started without infection, they're fine, but some started with infection.
Yeah.
Okay, so you would kind of see the whole of population behavior in the locked houses, for example.
Okay.
It's still loose, but these are kind of, the discrete models. The chapter, we're going to get into chapter EM3, and that's really the what we call the general epidemic.
Okay.
That's EM3. Okay.
All right. Thank you.
Sure. Okay, everybody. So take care and be in touch. Bye-bye.